Okay, so this is where we paused before. So looking at how light diffracts as it goes through a double slit or multi-slit grating. So this is the formula we use for all those situations, but it also works for a single slit. But be careful on a single slit, because it works differently on a single slit. On a single slit, it's the same formula. However, this is the width. This D is the width of the entire opening of the single slit. And the M as a 1 is the distance to the first dark spot. It's from the central maximum to the center of the first dark spot. A 2 on the M is the distance to the second dark spot. A 3 on the M is to the third dark spot. That's for a single slit opening. Now it gets stranger. So let's say if you're trying to measure the width of a hair. Well, the width of a hair is not a double slit. It's not a multi-slit. Is it a single slit or is it more like a double slit? You might think it's almost more like a double slit because the light would bend around the hair because the wavelength of light is similar in size to the hair, a little bit shorter, but it can still bend around the hair. It actually acts as a single slit opening. The way the light bends around the hair, it behaves as if the hair was an opening, a single slit opening. So it turns out we use this formula to measure really small things, but you got to know how to use that formula in different circumstances. This formula is used for a double or multi-slit formula for the M being a 1, 2, 3, or 4 for the bright spots, or for a single slit opening or measuring a single item like a worm maybe or a single strand of hair as a integer to the dark spot. So it works differently for a single opening or a single strand of hair. So let me be clear. If you have a single slit opening and M of 1 measures to the first dark spot, not to the first bright spot, to the first dark spot. If you're measuring a hair off of your head, you put it in front of a laser. It will make a diffraction pattern on the wall. But if you want to find what the width of that is, which is the D would be the width of that hair, you would measure to the first dark spot as an M of 1 because that hair actually acts as a single slit opening. Even though it's not an opening, it behaves like one. So keep that in mind when it comes to the AP test because that's something you just got to memorize. There's not a lot of things you got to memorize in physics. That's one of them. This formula works for all that diffraction stuff, but the M of 1 is for the dark spot if it's for a single slit opening, but an M of 1 is to the bright spot for a double or multiple slit opening like in a diffraction grating. That you just have to memorize. Alrighty. So this whole thing is for a multiple slit, a double, not for a single. That was just a little PSA on the single, just so you understand, keep your heads up looking for if you run into a single slit opening, it is the same formula, but an M of 1 is to the dark spot, and a 1.5 would be to the first bright spot on a single slit opening. Okay, back to the multi-slit because it's a little more popular than the single slit opening. So an M of 0 would be to the first dark spot, which would be to the half. An M of 1, 1.5 would be to the second dark spot, and so on. And you might use that to help you find your angle, so you could plug it in and find either the width of this, or maybe you don't know what wavelength of light you're using. You try to identify what wavelength of laser you have, but you know that you're spacing on the slide that you're using on your diffraction grating. So you already know what the spacing is, so you want to go back and identify for sure what wavelength of light you're actually using. Okay, So largely we use diffraction to measure the size of really small things. So a lot of times we're solving for the D. We know what size of laser wavelength we're using, and so we measure what angles we're using to measure how small things are. That's what we're doing with diffraction normally. All right, onward and upward. So here's your lone example. We have a viewing screen that is separated from a double slit source by 1.2 meters. The distance between the two slits. So that's your D. So we actually already know, the D on the opening is 0.03. The second order bright fringe, which is an M2, is 4.5 centimeters from the central maximum. That's in the middle. So in this case, we don't know the wavelength of the light. We're solving for the wavelength. Alrighty. So we know the distance to the screen is 1.2 meters. That's what this tells us. That's the distance from the slits to the screen. So first thing, let's find your angle. Okay, so if you're wondering what exactly we're doing here, so let's say there's your slits of your light. The distance to the screen that way, that's your 1.2 meters. And as your light comes through, there's your central maximum right over there. And then you got a bright spot, then you got another bright spot over here. And that bright spot to there, that is your 0.045 meters. Got to remember to be in the same units for everything. So since we're in meters for the 1.2, we just will be in meters for everything else. So hence, when we're doing your tangent of your angle, let me switch colors, or not switch colors. Let's go to that. So if I'm doing my angly stuff, there's your 1.2, there's that. And so, whoops, that's a terrible angle. But there you go. You're just solving for angle theta. So that's what you're doing over that angle. The tangent of that angle is your y, your 0.4045 over 1.2. And let me just stop drawing. I'm not doing you any favors with that, I don't think. And there it is, 2.15 degrees. Make sure you're in degrees when you're doing this stuff on your calculator. Make sure you're not in radians and you just came in from calculus class or something, had your calculator in radians. Make sure you're in degrees. So 2.15 degrees. And now what do? Well, you plug it into that other equation. That one right over there. You're solving for the wavelength, right? So you've got the D, but remember, you're not in meters. You got to go 3 places over with that thing. So you're already over there, and you got to go 3 more. That's why it's 10 to the negative 5th. Then times sine of 2.15. Then you got to, since it's the second order maximum, it's the 2, divide out by the 2, and wait for it, bam. So in nanometers, that's 562. Because nanometers would be -9, which is the common way to say that. So greenish, that'd be like green light, 562 nanometers. That's kind of a popular laser thing to do these days. Questions, guys? Anything? Anything? Alrighty, that ought to... Oh, wow, you get a double. I didn't know there'd be 2 problems. I thought you only had 1. It's a bonus day for you guys. All right. So here we go. So this is purple, guys. A little purple nurple. Well, blue purplish. It's pretty purple. So there's your wavelength, falls in diffraction gradient. A lot of slits. Now we're going to find for how far apart the slits are, I bet. Yep, 1.8 meters away between the dark fringes. On the screen is 1.8 meters away. Distance between the dark fringes on either side of the bright central is 4.2 meters. Okay, so we're doing the dark fringes. Remember how to do that? What's the separation between the slits? We're looking for the D thing. All right, so now we're doing that tangent thing. So remember, if I do a quick setup for you, I know how much you guys love my pictures. Okay, So the length of that thing is 1.8. Now we're only going to the dark side over here, and the dark side is the 4.2, so 0.0042 meters that way. And then you got to find that angle, so that's the tangent you're doing. So the tangent of that angle equals a... Where the crud is the 0.0021 coming from? Am I nuts? Distance between the dark fringe. Oh, they're doing the halvesy. Oh, you have to be a reader to do this job. So the dark fringe here and here is 0.042, making that a 2-1 to there. I don't know why they just tell me it's 2-1. Fleas are back. Those things that fly around, fruit flies, whatever. So that's why it's the 0.0021. It's, there you go. Whatever. Alrighty. Get rid of that pin. And you get to 0.067 degrees. So it's pretty exciting stuff there, guys. And then you plug that back in and you solve for the D. Alrighty. So you're solving for the D. But remember, you're doing the first dark fringe, so the M's is 0. So that's a half. And so it's a half. And it's 450 times 10 to the negative 9th. Blah, 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 blah. You get it. There you go. Now that's the distance. That is the distance. What are they looking for? Okay, that's it. The separation between the slits. Oh, how many lines per meter? So how do you do the lines per meter? Flip it. Flip it good. So that's the meters per line, right? That is the meters. That is the meters per line. That's what that means. Meters per line. So if you want lines per meter, you just flip it. 1 line per that, you just do the inverse of the thing. And you do the inverse of the thing, and boom, you get 5,192 lines per meter. There it is, guys. So the way they made that diffraction line is they made a little etching in there, and they made 5,197.2 lines per every meter. That is one big diffraction grating. It's probably not that big. Anyway, so that should be pretty much it, guys. Any questions? Give you less than 3 minutes to ask. You're down to 2 minutes. Oh, we'll give you 2 minutes to ask any. You're not going to ask any questions. All right, that's the end of that, guys.